like Wednesday.
Next Wednesday. Oh, next Wednesday. That's right. Yeah, Wednesday or Monday. Probably Wednesday. Okay, let's take a look. So pay attention to it. Right, mainly quiz. The R-2R DAC. Right. So a very simple example looks like this. It's not doesn't have as many bits as we have, for example, on the, in the lab. But this will be able to teach you how this works. 1, 2, 3 resistors in here. 2, 3 output. One more here. 2R. 2R, R, 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 2R, 2R, 2R. Here's VL. Okay, and these are digital inputs. If I label this D0, D1, D2, D3, I can tell which one is the LSB, which one is the MSB, right? LSB, MSB. Okay, let's do the calculation. You'll be able to tell why. The reason for that is if you apply a voltage here, digital voltages, because it's a digital circuits, right? So the digital voltage here means 5 volts. If it's a 1, logic 1, it's going to be 5 volts. Okay, if I put logic 0 here, it will be 0 volts, which is ground. Okay, so for example, if D3, D2, D1, D0 is 1, 1, 1, 1. Okay, so 1 means 5 volts. 1 is 5 volts. How do we run the calculation? So the way to do that is superposition. So we can do D3 only. If only D3 is functioning, so we ground all the other sources. So the circuit looks like this. Here's the 2R. 1, 2, 3. V out. So we got 5 volts here. Oh, 2R here. R, 2R. Ground. Keep in mind, because all the other sources should be grounded in superposition. If you only have D3 functioning, so that D3 only apply D3 to the circuit. So all the other ones should be grounded. 2R, 2R, 2R. Okay, pretty simple because the D3 is just on the right hand side of the circuit. And it can definitely combine all these other resistors into one, right? How? Are they just parallel resistors? If you, starting from this point, so these two terminals are both grounded. So they are parallel resistors. So 2R, 2R in parallel will be what? Is that 1R, right? The 1R here. And in series with this R, it will be 2R. So what's the overall resistor here? Resistance? 2R, right? Because this is 1R in parallel. 1R plus 1R will be 2R. Okay? So this thing can be replaced by a 2R resistor from here. And then you start looking at this circuit. It'll be 2R, 2R in parallel. Okay? So it's going to be 1R again. 1R again. And in series with this R will be 2R again, right? Okay? So got 2R here. 2R for everything here. 2R in parallel will be what? 1R. Any questions on this before moving forward? Easy, right? So 1R, 2R, right? 2R in parallel. So what's the VL over here? It's a voltage divider circuit. What is VL? What is it? 2.5. Yeah? Any question on this? So what about D2 only? So this will be grounded this time. D2 only, so 5 volts here. Ground. What is VL this time? So this part is pretty simple, right? So we're getting 1R, 2R, 1R, 2R. So eventually this can be converted to a 2R resistor. Have this guy here as well, right? Okay, what's next? You are saying, hey, here's a voltage divider. Is that correct? Why? They don't have the same current, do they? Does this guy and this guy, do they have the same current? No. So can I use voltage divider theory? No. So how can we do that? It definitely is pretty simple resistor network. In circuit 1, you have deal with so many different resistor network circuits. You know, it's very simple. You can use mesh. You can use so many different theories to solve for that. But for this time, we're just looking at the terminal over here. The terminal over here to ground this terminal. If you flip it, can you treat the circuit like something like this? 5 volts. 5 volts, 2R, no problem here, right? It's the same circuit. 5 volts is a battery. It's a power source, definitely has a ground. So it's a common ground with this ground. So eventually, it's a 5 volts, 2R, and then it has a terminal connects to the load, which is whatever connected to here. That's a load. Okay, this is this resistor, you rotate it like this, right? So you got 2 terminals, and whatever after that will be the load, right? Will be the load. Let's treat everything after this point to be the load. And this circuit will be this circuit. Do you agree with that? Okay, so let's do a Thevenin's equivalent. So for this thing, if we looking backwards, the RTH becomes what? RTH. Because this guy is shorted, right? So RTH is looking backwards from the terminal, because whatever after terminal will be the load. Here's the load here, okay? So let's looking backwards. Remove the load. Remember, Thevenin's equivalent, remove the load and looking backwards. So here's the RTH is 1R, right? VTH is what? You're still not comfortable with voltage divider? Here we can do it. Why? Yeah, since the load is removed. The load is gone. So the load is gone, then the current will be the same. So we can do a voltage divider. So VTH is what? A half, right? 2.5 volts. So eventually this part of the circuit, starting from this node, right, we can convert this circuit into its Thevenin's equivalent. So eventually this becomes 2.5 volts and a resistor in series with it, which is RTH. So RTH is R, and this is 2.5 volts. Or let's say 5 volts divided by 2. You agree with that? So these terminals, look at this terminal. Let's label it A, B. Okay? And then here's A, here's B. It's equivalent. Here's A, here's B. Since they're the same terminals, I removed everything here and I converted to its Thevenin's equivalent, and now I know these are still the same terminals. I can plug it back in. So if I plug it back in, I'm getting 5/2, which is 2.5 volts, with 1 R, right? So plug it back in here, and I got another R here, and 2 R, and BL. Okay. This looks pretty easy. And now they both have the same current, so it's a classic. No, it's a really standard voltage divider circuit. So what is VL here? 5/4, right? 5/4. So what about D1 only? So you can see every single digit for this DAC. So every single input for the digit of every single digit of the input is contributing a certain weight to the final output, and you eventually you superimpose all these results into one overall VL to get a final result. That's how that works. So what about D1 only? Let's draw the circuit again. Grounded because D1 only, D3 is not working. Oh, D1 only, so here's 5 volts. Ground. Can we combine these resistors first? No, because current still keeps flowing. Okay, so we have to start from here. Can we combine these two? Yes, they're in parallel. Okay, grounded, both grounded in parallel. So the overall resistance of these two guys will be 1 R. So 1 R here, add to another R will be 2 R. Okay, 2 R. So from here, 2 R. This whole thing is 2 R. Then you look at this circuit. It's the same problem. Same problem. You use these two terminals as the two terminals and run the Thevenin's equivalent calculation to get RTH and VTH. So what's the effective voltage being applied to here? No, sorry. Yeah, let's just convert to Thevenin's because you don't know the voltage here right now, as of now. So this circuit, you treat these two terminals as a output terminal, and you remove the load looking backwards, like what we did over here. Remove the load looking backwards, you can get RTH, and use the volt divider theory, you can get VTH, and then connect that Thevenin equivalent circuit back to the terminal, and you're getting this. Here, right, the terminal, RTH is R, VTH is 5/2. Okay, and then you got another R, 2 R, R, 2 R, V out. So what's next? It definitely combines these two. as one big resistor, 2R. This is 2R. What's next? We are facing the same problem, so let's do that Thevenin's equivalent conversion one more time. Because here you got one 2R resistor, another 2R resistor, and you got an output network here. That's the two terminals. Two terminals, even though I didn't draw it, but you can imagine this is two terminals. And here's the load. That's the load. But it's grounded up here. But if I flip it, it's probably more comfortable. You got a ground under here, but it's the same thing. So you got this is the load. Remove the load and looking backwards. So we got parallel resistor 2R. Eventually it's 1R, and the voltage here should be divided by 2 because it's a voltage divider. After the load is removed, the two resistors will have the same current. So eventually the output terminal voltage will be 5/4, right? So eventually this part of the circuit can be converted to 5/4 R, and add this R here, that's another R, and then have 2R here, and here's V out. So what is V out in this case? 5 over what? 2R, right? It's getting divided by 2 one more time. So it's divided by 8. Right? Okay. The last one. D what? D0 only. So D0 only, so all the other sources should be grounded. But only has D0 has 5 volts over here, and the 2R, R, R, 2R. Okay. If I ask a question, right, this could be an interview question. So what's the resolution of this DAC? So 5 volts is the voltage reference, which is the overall voltage range. But whenever they're asking for a resolution of the ADC or DAC, what are they expecting? Are they expecting a minimum voltage that's going to resolve, or how many bits of the device has? Is it how many bits, or so what's the resolution of your ADC? So you're telling people, hey, we designed ADC in our VLSI class, okay? So whoever interview you will ask, so what is the resolution of our ADC? So that's, your answer should be how many bits. So for this DAC, how many bits do we have? What's the resolution of the DAC here? How many bits? 4. D3, D2, D1, D0, right? Okay, so if you have 5 volts as an overall range, and so what's the minimum change, an analog voltage change at the output this DAC can make? So which means it's a 5 volts over the total range, which is 5 divided by 2 to the 4th power, because it is able to handle 2 to the 4th different combinations. So it's actually resolving that 5 volts range into this many steps. Okay. So if you look at the V out, this is the minimum change the V out can resolve or can make. Right. So here's the LSB. So the LSB means every single one change over here should cause a minimum analog voltage change over here. So that becomes 5 volts divided by 16. So before we do the calculation, by looking at this one, so for D1 only, we are getting this, right? So when we have D0 only, you can expect what's going to happen. Okay? So you can expect D0 only. A digital 1 change at D0 will give you a 5 over what change as the analog output? 16. Now let's verify it. So here, very simple. 7 is equivalent. 5 over 2. Look at this terminal. It's going to be R, another R, right? R, R. And do it one more time. Let's do the same circuit. But I can convert this one to wait, 2R, 2R. So this one should be is that correct? Okay. So this becomes, if you just look at this point, 5 over 8 here's VL. This one still have this guy here. This is grounded. 2R, 2R. Oh, is that correct? No, this is already converted to this guy, so this is not existing anymore. So got R, R. So eventually it becomes, oh, so it's a divider, so this one equals 5 over 16. So if I give you a circuit looks like this, give an arbitrary input, one zero one zero. It's on the quiz on Friday. Can you solve for this problem? Just go through all the steps, but probably not 4 bits, maybe 3 bits, those kind of things. Expect a quiz on this, right? I think it's on Friday. It's either Friday or Monday, but any questions on this before we move forward? We're good? Okay. 2, 3, 4. So let's talk about this is 5. Let's talk about resolutions, ADC and DACs. Give you some examples. For 0 to 5 reference voltage for sensor, there's the analog data input, right? Here's the ADC. We're talking about ADC this time, not DAC, okay? ADC. Analog to digital converter. Here's the analog input. Here's ADC. So eventually there will be a digital output here. And it's requiring this ADC to resolve 1 millivolts change of the analog input. And you know that the reference voltage is 5 volts, or Vref is 5 volts. which is the total range of the voltage change. So don't worry about the circuit structure for now. We are not talking about that for now. So just looking at these parameters. If this is a voltage range, you want to use this one as a total range of the voltage change, and 1 millivolts will be the minimum voltage that this ADC can resolve. So it's going to ask you how many bits are required to resolve a 1 millivolts change from the analog input. So how to do the calculation? How to calculate it? So how that works is like, for example, you have a 0 to 5 volts range for the ADC, and it's trying to resolve this whole range. For example, it's a 10-bit. Okay, it's a 10-bit ADC. So what's going to happen is there will be 2 to the 10th little steps that this ADC can resolve within that range. All these little steps. But anything lower than 5 volts over 2 to the 10th, this is somewhere around like 5 millivolts, right? So anything lower than 5 millivolts cannot be resolved, which means if there's a like 2 millivolts change from the sensor analog input, the ADC will not be able to resolve it, cannot sense it. It's pretty bad, right? So when we are doing a digital design, you want to look at the minimum voltage change of the input first, and then pick up the correct resolution of the ADC. So that's the goal here, okay, to understand that. So for example, 2 to the 10th is 1024, right? 2 to the 10th is 1024. So 5 over 1024 is somewhere around 5 millivolts. And I'm asking you to resolve 1 millivolts change. So is the 10-bit ADC not good enough for this design? No. So we need how many bits? That's the question here. How do we calculate it? You don't like direct guess, right? 11 bits, 12 bits. So we need some numbers, and tell me why. So you are not overshooting. Why? Because a very precise ADC probably costs more money. As long as it's good enough, we don't really care, right? You don't need a 20-bit ADC. Too much is overkill. So how do you do the calculation? It's very similar to one of the problems in the homework. So it's 5 volts over the whole range, or you can use the ratio. Right? 5 volts versus 1 millivolts. Because 5 volts is the whole range, let's say how many bits? I don't know. 2 to the x power. This is how many bits you have over 1 LSB. Because 1 millivolts represents 1 LSB change. And totally how many LSBs do you have? 2 to the x power, which is how many bits do you have? Any question on this? 1 LSB, just the 1. There's no unit, just the 1. This is how many LSBs do you have, right? 1 LSB should represent 1 millivolts, and this is the total range you have, total voltage range you have over there. So 5 volts versus 1 millivolts, and the total number of LSBs versus 1 LSB. So you run the calculation, eventually probably need a calculator. This becomes 2x power will be 5,000, right? You'll do a log based 2x equals this. Okay, so x equals this, and just do the calculation. And eventually we are getting 12.288. So how many bits do we need for this ADC? 13, yeah. 13, right? So let's look at another example here. For DAC, any other papers, just grab one of these papers. All right. For a DAC, remember the DAC we just went through? So there will be a full scale range or full scale value of the DAC. So let's look at the DAC. So for this DAC, what is the maximum output or full scale range do we have? If I have all ones, what's going to happen? What's the maximum output voltage we are getting here? So actually it's not 5 volts. I can tell you, it's not 5 volts for the full range. So the full scale range will be, let's say, if I have ones for each single digit input, what's going to happen for the output? It'll be 15, right? 15. So this is going to be 5 volts over 16 times 15. So it's actually not 5 volts eventually for the output. It's 1 LSB less. Did you get that? So you're not eventually getting 5 volts for the output, even though you have 5 volts as a range or as a digital logic 1, but eventually the maximum VL will be 5 over 16 times 15, because whenever you have ones for each, it's still not giving you the entire 5 volts at the output, just by the calculation. Is that correct? Do you agree with that? Let's verify it. I mean, it's very simple, and do we need to verify it? But so, for example, when we do the superposition, you give a 1 to each, and eventually we are getting 5 over 2 plus 5 over 4 plus 5 over 8 plus 5 over what? 16, right? And eventually this becomes 16 is A plus 4 plus 2 plus 5. Is that correct?
No, plus 1.
Oh, plus 1, yeah, times 5, right? So this becomes 15 over 16 times 5. So that's the final result. If you have all ones, it's not giving you 5 volts. It's going to be 1 LSB less. Keep that in mind. So that's the full scale DAC output eventually. All right. Here's an example. I think it's very similar to the ADC one, so we probably don't have to go through this example for the DAC. So let's directly look into the table here. Yeah, this is also very simple. We don't need it. I don't think we need it. All right, let's probably just directly run the quiz. Okay. Some of you might be able to get it done really quickly, but we'll see how that works. Give you a little bit more time to work on it.